Welcome back. In today class, I am going to discuss about the spaces of vectors and some examples related to the vector space. In the previous class, what we have observed that a vector space is a composite object consisting of a field, a set of vectors, and two operations with certain special properties. So we have defined vector space in the following way. So I have vectors V, F is the field, and we have two operations that is called vector addition and scalar multiplication. So this composite object, so this is some kind of composite object, and we have given the name of this whole composite object as a vector space or a linear space. One important point I am going to highlight here: the same set of vectors may be part of number of different vector spaces. Okay, so we will see these point on the next part of this course. So I am going to note down this point because this point is very important. So remark is like this: the same set of vectors may be part of a number of distinct vector spaces. It means that using same set of vectors, I can define different vector spaces. One more important point I am going to highlight here: when there is no chance of confusion, we may simply refer to the vector space as V. So instead of writing this composite object that contains the vectors, after that field and two operation, I am going to denote this whole composite object just by V. So underlining field and addition, vector addition, and a scalar multiplication is the implicit inside that notion V, or when it is desirable to specify the field, we shall say V is a vector space over the field F. Okay, so this is again the second remark. So notion of vector space I am just going to represent by V. I am not going to represent by composite object. And in note I am going to write this. So as a note, when it is desirable to specify the field we shall say V is a vector space over the field F. So we are going to say this particular statement: V is a vector space over the field F. The name vector is applied to the element of the set V, and that is largely as a matter of convenience. I have already told you that vector space or whole vector space based on definition can be expressed as a composite object, but for our convenience just we are going to use this notion of vector space as a V. If we have no confusion on the underlining name, then I am going to proceed the further part of the vector space. So I am going to start the vector space with following definition. Again, I need some more definition, so I am going to state that definition. So definition is like this: the space Rn consists of all column vectors V with n components. So several times during the mathematical modeling I was talking about the space, and if you remember, then I am denoting one class of system that is called autonomous system, that is like this: x dot equal to fx, and I am using this kind of notion: x belongs to Rn, and this function f map from Rn to Rn, and I have initial condition that is again lie on Rn. So this is the representation of autonomous system, and basically this system is evolved in n-dimensional space, and we have already seen that x belongs to Rn is nothing but I have certain kind of column vector that has n number of element, and I am assuming that all element x1, x2 and xn are the real number, because we have already seen that whenever I have any system, so and we are giving certain kind of input and we are expecting certain kind of output. So here suppose I am providing the initial condition and I want to monitor the trajectory, then both x0 and xt represent the some kind of column vector with n component. Okay, and since input data and output data is always certain kind of real number, so due to that reason I have denoted x belongs to Rn. Let us come to one example of this particular space. So example is R5 contains all column vectors with 5 components. This is called 5-dimensional space. So you can see here that I can visualize the space, and suppose I have to visualize the space R1, then I can draw one real line. So this is our origin, this is minus infinity, and this is plus infinity. So meaning of R1 is that our column vector have just one component, and that component may lie anywhere on this particular line. Similarly, meaning of R2 so this time I am going to take the two real line. So I am going to denote this as a x1 and this as a x2. Sorry, so basically this particular axis I am going to make this particular axis as a x2. So R2 contains all column vector with two component, and this is called two-dimensional space. So suppose I have some point P, so I can represent that point like this, x1 x2 as a column vector, or equivalently you can write like this, x1 and x2. Similarly, I can denote the three-dimensional space. So now I have to take help of three real lines. So, and I am denoting this as a x1 and x2 and x3. So any point on this space P can be written like this. So R3 contains all column vectors with three components. This is called three-dimensional space. Now, if someone asks me to visualize R4, R5, Rn, it is very difficult. It is very difficult to draw on the whiteboard or blackboard. Now, if question is like this, if we are unable to visualize something, then how to think about that? And somehow here contribution of linear algebra comes into picture. So I am going to write this important observation using some remark, and why this remark is important? First we will write the remark, and after that we try to understand the meaning of the remark. The great thing about linear algebra is that it deals easily with higher dimensional space we do not draw the vectors in the higher dimensional space. We just need the some finite numbers. So now in order to deal with 5-dimensional space, there is no need to draw it. Just you can take any 5 numbers and put that 5 numbers inside some column vectors, and that is 5-dimensional space. Similarly, I can deal with any dimensional space, and due to linear algebra it is possible to generalize any result, whatever result. Suppose that you are doing analysis of first order system, so you can able to visualize or extend first order system into second order, similarly in third order, or even if in fifth or nth order, without knowing that how to draw the vectors. That is the one of the important contribution of the linear algebra for the our purpose. So let us try to note another important point. I have already discussed about this, but for the sake of clarity, I am going to write here the vector R2 is represented by the usual xy plane, because we are very much comfortable with xy plane. Each vector v in R2 has two components, and that is x and y, or x1 and x2. The word space ask us to think of all those vectors the whole plane and each vector gives the x and y coordinates of a point or position in the plane. So V is denoted like x and y. So somehow vector space gives the broad picture of the coordinate of some point. So suppose that if we are dealing with 5-dimensional space, then I have 5 different coordinates of a single point in that particular space. That is the meaning of the space. So similarly, in Rn space, I have n number of different, or it might possibly it is same in terms of number. We have n number of coordinates. One more important point I am going to highlight here. So several times I am using in this course. So I am going to write in form of remark. That is, I was talking about real vector space. Real vector space, and I have already told you several times why we are just focus on the real vector space, because I have most of time I have machine, and whatever observation or whatever experiment I am going to apply to that machine, in order to measure that input, I need some kind of realistic device, and whatever data that is reflected on that device, that is some kind of real number. Whatever output I am getting, in order to measure or track that output, again whatever device I need, that is able to give some kind of real number. So due to that reason, our inherent field inside the vector space is some kind of real number. So due to that reason, I have add one more terminology with vector space, that is called real vector space. So I am going to define it clearly in order to avoid any kind of confusion. So a real vector space is a set of vectors. Obviously I have vector space, so I have certain kind of vector together with rules for vector addition and for multiplication by real numbers. So this is the story about the real vector space. Now I am going to take some more example which is different than vector space, which is denoted by Rn. So here are three vector spaces other than Rn, and we will see the motivation also. So first one is denoted by M. The vector space of all real 2 by 2 matrices. So first example, now I have no column vector. I have some kind of vector which contain 2 by 2 matrices. Similarly, I have another example. I am denoting that by F. So here, please do not confuse. This F is for function, and whatever F I am using for field, that is little bit different than this F. So the F is the vector space of all real functions, that is denoted by Fx. So here element of the vector space is some class of function. In first example, element is matrix. In second example, elements are the functions, or vectors are the functions. And third example is very interesting. So that is denoted by Z. The vector space that consists only a zero vector. So now I have third example where vector space has just a single element, that is zero vector. So in the first example, M, the vectors are really a matrices. In F, the vectors are functions. In Z, the only addition operation is defined, that is 0 plus 0 equal to 0, because just I have single element. So all other thing is very obvious. So you can see here in these all three examples, I am no longer just dealing with those kind of vector which has just a column. In each case we can add, in case first we are adding matrices to matrices, in case 2 functions to functions, and in case we are adding 0 to 0, we can also multiply a matrix by some number. You can assume any number, 4 or something. In second case, I can multiply that number with function, or same number I can multiply with the 0 vector. After multiplication or addition, one can observe that the result is still in either M or F or Z. So these all condition of the definition of vector space one can easily check, even if we move from the column space to those kind of space where we have matrices and we have functions, and even if we have 0 vector. In the latter part of this course, I am going to talk about the dimension. Before talking the dimension, you have to believe on me, and I am going to take one example. So if you see the function space, whatever I have selected as example number 2, that has infinite dimension, and we will see why I am telling this as a infinite dimension. So I am going to write that example. The function f is infinite dimensional a smaller function space that is denoted by P, or in some book that is denoted by Pn, containing all polynomials. So actually function space is infinite dimensional space, but it is possible to create some kind of functional space which is just a finite dimensional. Suppose that if you consider some kind of a space where we have polynomials, and I am going to define that polynomials P n like this: a0, a1x, a2x square, and plus a n x power n of degree n. We are telling that this polynomial have degree n because the highest power of this polynomial is n. So similarly, I can truncate this polynomial up to 2, and then we can tell that this is again some kind of finite dimensional space or a smaller space. Why I have taken this example? Because some of you may aware about the Laplace transform. And what is beauty of Laplace transform? It can convert differential equation in algebraic equation, and there you can observe that if I have higher dimensional differential equation, then I am getting some kind of higher dimensional polynomial. So polynomial is also one of the example of the vector space. And what is underlying field? Again, underlying field is real number. One more remark I am going to write here, and that remark is basically based on the smallest possible vector space. So basically Z is the smallest possible vector space, and I am going to denote that vector space by r power 0. So, and this space only contain the 0 vector only. So I am denoting that 0 vector by this point. So this is the smallest possible vector space. And what is the largest possible vector space? We have already seen that is the function or some more thing which will satisfy the property of, or property means vector addition or a scalar multiplication. But here one of the obvious vector space which is of the largest, one can interpret that as a largest possible vector space. So one of the example is function space. One more important point I am going to highlight here, that is like this. So it is important to note this point. No space can do with 0 vector. We have already seen this from the definition, and each space has its own 0 vector. For example, in case of matrix the zero vector is the zero matrix the zero function in case of function space, the vector that is denoted by 0 0 0 in R3. So we have already draw the pictorial representation of column space. So now let us try to draw the pictorial representation of four-dimensional matrix space. So using this picture, it is possible to understand that even if our vector space contains some kind of matrix or some kind of function, it is possible to somehow draw their pictorial representation. But this is not true for each and every time. So I am going to draw the following, that is four-dimensional. Again, please be careful, I haven't defined what is meaning of dimension. So matrix space M. So in order to draw that space, I need four component. So I'm going to denote four component, that is like this. So one component is like this, another component may be of like this, another one is like this, and last one is like this. So here order doesn't matter. And now suppose you have to draw any general point in this four-dimensional matrix space, then I can draw like this. Suppose I have to visualize this point in this space. So basically this point is A, B, C, D. So this is basically typical vector in M. So in this way, somehow we try to visualize the matrix space on the whiteboard or blackboard. Now let us try to come to some standard example for the vector space, because now we are able to understand what is meaning of a space. So somehow meaning of a space is related to coordinate, and we have also observed that a space may contain any kind of function, any kind of matrix, any kind of column vectors, even if we have just one vector. Most of the engineering problem, particularly which deals with differential equation or algebraic equation, concept of a space Rn is involved, where R is the real number, but sometimes for analysis purpose we are also using the complex number. So now I am going to denote the space not by Rn. Now I am going to denote a space by something more, where now we are also giving some flexibility on the field. So actually I have collected some of the examples on that perspectives. So I'm going to talk about example. First example, so that is called the n tuple space, and this space is denoted by F. So if this field F is a real number, then that space is called real space. If that is complex number, then that is called a complex space. Sometimes this field may be anything, provided that will satisfy the axioms of the field. And we have already seen that how to check that some particular thing satisfy the property of field or not. Okay, so in order to generate n tuple space, if you are moving beyond real number and complex number, first step is please check that whatever underlining field you are going to take, that will satisfy the axioms or field or not. So I am assuming that whatever field I have selected, that is not going to violate the proper axioms of field, and based on that assumption I am going to create this space. And what is meaning of n tuples? Meaning of n tuples here, that in this vector space I have n number of component, or means each vector is denoted by n number of component. That is the meaning. So let F be any field, and let V be the set of all n tuples, and I am going to define that n tuples by alpha. So, and that is x1, x2 and xn. So either you can represent by column vector or row vector, that doesn't matter, of scalars xi in f, in field f, if beta, that is denoted by y1, y2 and yn, with yi in field f, the sum of alpha and beta is defined by alpha plus beta, that is component wise sum, so here you can see that I am talking about the generalized n tuples space. So suppose if field is complex number, then we have to talk about the sum in terms of complex number. So this is about the addition. Again, we have to specify the multiplication also. So the product of a scalar C and vector alpha is defined by like this: C into alpha equal to Cx1 Cx2 up to Cxn. Now I have to check that all property of vector addition and scalar multiplication of the vector space should be satisfied, and it is not difficult to check that this property is obvious. So due to that reason, we are telling that n tuples space is nothing but some kind of a space where f is the field and vector has n number of component, and if I am able to define vector addition in this particular way and scalar multiplication in this particular way, particularly I am defining in the component wise. Similarly, I can talk about the second example. So I have example 2. The space of M cross N matrices, and this space we are going to denote by this. Here underlining field is again f, so f can be real number, complex number, and again maybe anything, just that should be satisfy the axioms of the field. So let f be any field, and I'm going to denote f like this, and let m and n be positive numbers. Let f m cross n be the set of all m cross n matrices over the field f. So now we have identified the vectors, we have identified the field. So now I have to identify the operation. How basically we are defining the operation, that is also important. So the sum of two vectors, here you can see that vectors is nothing but matrix A and B in this space is defined by A plus B ij, so ith and j component, so that is aij plus bij. After defining the sum, we have to also define the product. So I'm going to define the product. The product of a scalar C and the matrix A is defined by CA ij, that is equal to CA ij. So in this way one can define the space of M cross N matrix. For our purpose, here F is the real number. Another example which is frequently encountered during mathematical modeling, that is the third example. So I am going to talk about the third example. the space of function from a set to a field. We have already seen that whenever we are talking about the nonlinear system, then right hand side is the function of states in case of autonomous system. In case of non-autonomous system, that is function of time as well as the state. So basically my state x1, x2, x3 and xn is somehow belongs to some kind of function. So we have to talk about the space of function, and underlining field in case of our analysis is real number, but in case of generalization it may be anything. So now I am going to define the field, vectors, operations in this particular space. So let f be any field and let S be any non-empty set. We are assuming that set S has at least one element. Let V be the set of all functions from the set S into F. So this is the definition of the space. Now I have to define the two operations. So the sum of two vectors f and g in V is the vector f plus g that is the function from S into F defined by, same like previous two example. Once you identify the vectors underlining field, then you have to define two operations. First operation is the vector addition, and after that you have to define the scalar multiplication. So f plus g is defined like this: fs plus GS. The product of the scalar C and the function f is the function CF defined by CF So in this way we are defining the vector addition and scalar multiplication. Suppose that your field is real number, then interpretation of the sum is the pointwise sum of the real number. And what is interpretation for the multiplication? That is the pointwise scaling of the point, some point by amount C. That is the interpretation of the product in case of function. Similarly, we can give different interpretation if our underlying field is different. During the discussion, I have already told you that most of time in control system or in signal length system, we are dealing with the Laplace transform, where we have functions as a polynomial. So one can again define another space. So that is the example 4. The space of polynomial function over a field F. So again I have to identify the field vectors. After that the additions, vector addition and scalar multiplication. So let F be a field and let V be the set of all functions f from f into f which has a rule of the form, and we are specifying the rule like this: fx, that is c0 c1x plus cn xn, where c0 c1 and cn are fixed scalars in F, and we are assuming that that is independent of x. So independent of x. A function of this type, you have already aware about this, is called a polynomial function on F, and again addition and multiplication can be defined like the previous example, because this is again a function, and here one must observe that if f and g are polynomial functions and c is in some field f, then f plus g and cf are again a polynomial function. So due to that reason, this will also represent some kind of space. So basically in almost all engineering problems, we have four different spaces are extensively involved, that is called n-tuple space, and n-tuples space underlining field is real number. After that I have the space of m cross n matrix. After that a space of function from a set to a field. After that a space of polynomial function over a field, and these all are the examples of the vector space. In the next part of this course, I am going to discuss about some important question which is frequently asked by the students. So most of time students have confusion that if vector has no direction and magnitude, then how to visualize it. Second important part is that most of time students are thinking that vector space has four parts, means a set, a field, and two operations. Still do not understand what is vector space. Most of time they are thinking that they are knowing the addition and multiplication operation. Then why to care about these kind of abstraction? So these are some common questions. I am going to clarify in more extensive way in the next lecture. Thank you very much.